Let's now continue to understand the time frequency representation. Specifically, we are interested to understand this term over here, which is ej omega 2 pi over n k times n. What is this sequence? Where is it used? Well, if you look at this equation carefully, which is at the synthesis, this is the sequence that we are interested to look at now. In the synthesis equation, it clearly shows that to reconstruct x of n, we are multiplying ck for different k's, multiplying by ej 2 pi over n times k n. This is a complex exponential, and we'll now visualize it. This shows for n equals to 8, capital N equals to 8. For different small n equals to 0 to 7. And what does a complex exponential looks like? Well, I draw it for you. This is the real axis, and this is the imaginary axis. And the cross coming forward is time in n. So this is n equals to 0, n equals to 5, n equals to 10. So what is this? The first one, it is ej 2 pi over n, where n is 8 in this example, for different small n. It is this complex exponential that is rotating anti-clockwise. This is a 3D figure of it. The red dots over here is for different n. So this is n equals to 0, this is n equals to 1, n equals to 2, n equals to 3, and so on and so forth. So n equals to 0, 1, 2, 3, 4, 5, 6, 7, and 8. And you realize that at n equals to 8, it is at exactly the same point in the real axis. We can also visualize it in the real and imaginary part. So in the real part, we see that for n equals 0, amplitude is 1, imaginary part is 0. N equals to 1, this is the real part, this is the imaginary part. In fact, it forms a cosine for the real part and the sine for the imaginary part, because ej theta is equals to cosine theta plus j sine theta. So as theta is varying, we get the real part of cosine and the imaginary part as the sine. The third way to look at this is this polar plot. This polar plot can be imagined that you are looking here, and this is the eye. You are looking into a time. So time is coming forward to you, and you are seeing the change of your complex exponential, and you're visualizing it only in 2D. So this is n equals to 0. This is n equals to 1, 2, 3, 4, 5, 6, 7, and when you reach n equals to 8, it repeats and lands at exactly the same point. So now we can see the complex exponential in these 3 different ways. Now this is for k equals to 1. It rotates 1 complete revolution in n samples. What about for k equals to 2? So it's ej 2 pi over capital N times k divided by n. Now you see it, the 3D form, which is nicer. You'll rotate and you'll rotate again. So in k equals to 2 means it rotates twice. In k equals to 3, it will rotate 3 times in 8 samples. So here the k is showing you the k harmonic. The higher the k, the faster it is rotating. Right. The other way is that we have shown that it is rotating anti-clockwise when 2 pi over n is a positive value. Why is this so? Well, all you need to do is to plot the real and the imaginary to see that as n grows, the real part becomes smaller and smaller as n grows, while the imaginary part becomes bigger and bigger. So you see, this is the real axis and this is the imaginary axis. As n grows, the real part becomes smaller and smaller, and the imaginary part becomes larger and larger. So that's why we are rotating anti-clockwise. Now we also see that when we are using this in the DTFT synthesis equation, it is CK multiplying by this. CK, remember, is a complex value. We can represent the complex value by the magnitude and the phase, where CK is a complex number representing by magnitude and phase. So A plus JB can be represented as magnitude, and theta, where this magnitude is A square plus B square square root, and theta is equals to arctangent of B over A, where this is the angle and this is A and this is JB. So this is the magnitude and this is the phase. So theta is arctangent B over A, and this is the magnitude. Now when we use CK multiplied by EJ 2 pi over n kn, when we break it into the complex exponential notation, we can collapse the EJ theta to this, and we see that it is the magnitude multiplied by the complex exponential introducing the phase shift of theta. So that is why magnitude and phase shift is the important plot when we are doing the frequency representation. Thank you.